Today we are going to tell about the electric field intensity due to infinite long charged wire. See here, one charged wire is there, infinite long charged wire whose linear charge density is lambda. The electric field intensity due to an infinite long straight charged wire. Consider a uniformly charged wire of infinite length having a constant linear charge density lambda kept in vacuum. Absolute permittivity is epsilon naught. There is a point P at distance r from charged wire where electric field intensity E is to be calculated. See, this is charged wire. Infinite, whose linear charge density is lambda, and point P is there. At point P we have to calculate electric field intensity. By use of Gauss theorem we have to calculate, because I have told earlier that if you want to consider electric field intensity due to linear charge distribution or surface charge distribution, so there we cannot calculate by Coulomb's law electric field intensity, because there is a limitation of Coulomb's law. Coulomb's law will be correct for point charge, but when we will talk about the linear charge, Coulomb's law not valid. So we have to go through with the Gauss theorem. So see here, I have told you if you want to apply Gauss theorem, so firstly what we have to do, we will go for the linear charge density or charge distribution, linear charge whether surface charge density. Another I have told calculate or imagine a Gaussian surface, closed surface which is symmetrical, and where we can calculate electric field intensity by the help of geometry and symmetry. So for this what we have done, I have considered a cylinder, coaxial cylinder. This is the coaxial cylinder. Coaxial cylinder whose radius is r. Coaxial cylinder, the axis of cylinder and straight charge wire is same, and point P, radius I have taken r, so that point P lies on the curved surface of this cylinder. So this closed cylinder, we have taken plane, that plane is closed. So this closed cylindrical surface will be Gaussian surface for this charge distribution. So see here, imagine a coaxial closed Gaussian cylinder, surface of radius r, length I have taken, this length I have taken L, radius is r, closed at each end by plane caps normal to axis. This plane cap is normal to the axis passing through the point P. So see here, suppose this is the linear charge wire, long straight wire, this is charge. So I have make a Gaussian surface. So this, suppose this is the cylindrical, this cylinder I have make upon the axis of cylinder is the charged wire. See here like that. If you will see, that point P lies on the curved surface of wire. Here you can see, this will be the cylinder, this length I have taken L, this is the axis, and axis of cylinder is long straight wire. This is long straight wire I have taken. So see here, if you go for the symmetrical distribution, see here, this is the charged wire. If you go for the symmetry, so for this cylindrical surface, each point, if I am taking here I am taking this cylindrical surface, to see all points are at the same distance from this charged wire, at distance r, this point is also at distance r. If we'll see electric field intensity, magnitude of electric field intensity will be same at all points. First thing. Second thing, what will be the direction? If you will go for the direction, each and every point, this is the charge, infinite charge you have taken. So they are radially outward. For for this electric field intensity direction will be this, radially outward. Here also radially outward. Here also radially outward. Here also radially outward. If you see electric field intensity at point P, so this will be radially outward. And magnitude of electric field intensity at each and every point is this point. Also if you will see, so this will be E and radially outward. At this point if you will see, this is also E and radially outward. First thing. Second thing, if we are considering a small area ds on the curved surface, see here, this is the curved surface. I am considering a small area. Okay, that small area. So what will be the area vector here? Area vector, I have told magnitude will be the area, and direction of area vector is normal. So what will be the direction of vector ds? The vector ds has also perpendicular to the surface, that is also radially outward. So if you will see, E and ds will be parallel to each other at this curved surface. But when we talk about this plane surface end, if we see at the end, if we are considering any area at this end cap, plane surface, so if we see this plane surface, the normal vector will be, the direction of normal vector will be perpendicular to the plane or normal to the plane, and direction of electric field I have shown here. At any point if you will see the electric field, that will be radially outward. So this is radially outward to this. If you will see any point on the plane surface, this E and ds will be perpendicular to each other. Here also if you will see, the electric field will be radially outward, downward, E dash suppose magnitude, and you have considered any surface here ds, so direction of ds will be, so angle between this electric field intensity and ds will be 90 degree or perpendicular to each other. So one thing remember, for the curved surface if you will see, the electric field intensity and area vector or ds, they are parallel to each other, mean you can say angle between E and ds is 0. When we will talk about the plane surface end, what happen, E and ds is perpendicular to each other, that's why theta is equal to 90. So see here, consider a small area ds at point P on the Gaussian surface. By symmetry, the magnitude of electric field will be same at all points of curved surface, and the angle, they are directly outward, and angle between E and ds on curved surface, if you will see the angle between E and ds at curved surface is how much? 0. For plane surface what happen? For plane of cylinder E and ds are perpendicular to each other, E and ds perpendicular to each other. तो फॉर प्लेन सरफेस के लिए क्या होगा बेटा? फॉर प्लेन E and ds, theta is equal to how much? 90 degree. So see here, for curved surface E and ds are parallel to each other, theta is equal to how much? 0. And for these two planes E and ds perpendicular to each other, theta is equal to 90 degree. See here, if I am applying Gauss theorem, by Gauss theorem what happen? E dot ds for closed surface is equal to what? Total charge inside the Gaussian surface divided by epsilon. Inside Gaussian surface divided by how much? Epsilon naught. If you see LHS, left hand side, integration of E dot ds for closed surface. So this surface I am dividing into two parts. One is what? Curved surface, and another is what? Plane surface. This is curved plus two plane surface. Two end plane surface. Then total will be the Gaussian surface. For curved surface I have told the angle between E and ds is 0. So here E ds cos 0 for curved. For plane I have told you E and ds perpendicular to each other. So E ds cos 90 to plane. If you see here E ds, here cos 90, that is 0. This is for curved surface. I have told the magnitude will be same due to symmetry. So E you can take out, ds curved, and what will be the total area of curved surface? The length is L, radius is R, so that is 2 pi r L. LHS, total flux for the Gaussian surface. It is, I have calculated, this is E 2 pi RL. Why? Because for curved surface E and ds are parallel, plane surface E and ds are perpendicular. That's why flux passing through plane surface will be 0. Only for curved surface I have calculated E into 2 pi RL. If you will see RHS, 1 upon epsilon naught total charge. What will be the total charge here? If you will see total charge from here to here, lambda is what? Linear charge density, mean charge per unit length. And length is here L. So what will be the total charge? Charge per unit length is lambda, and length from here to here Gaussian surface, if you will see, that is L. So what will be the total charge? Lambda into L. ध्यान देना बेटा, यहाँ lambda linear charge density है, और in this Gaussian surface this length L is lie. Length L of the charge wire lie inside the Gaussian surface. So what will be the total charge from here to here? That will be lambda into L. So here total charge will be what? Lambda into L. By Gauss theorem, LHS is equal to RHS. LHS is equal to RHS. So E into 2 pi RL is equal to lambda L upon epsilon naught. LL cancel out. E is equal to lambda upon 2 pi R epsilon naught. E is equal to 1 upon 2 pi epsilon naught lambda upon R. Here you can see electric field intensity directly proportional to linear charge density. If linear charge density increases, electric field intensity increases, and one thing more I have shown, E inversely proportional to R. Electric field intensity is inversely proportional to R, not R square. In previous lecture you have seen for a spherical charge or for point charge, E inversely proportional to R square, but for linear charge wire E inversely proportional to R. See here, I have told you, if a linear charge density charged wire, infinite thin wire, suppose I have taken at distance R, what will be the electric field intensity? E is equal to 1 upon 2 pi epsilon naught lambda upon R. Okay, see here, suppose I have taken a cylindrical wire, hollow cylindrical, and we have given charge Q and charge per unit length also here. This cylindrical, not thin, this is the. Here also lambda is linear charge density. Linear charge density. Not surface charge density. Linearly they have given for this cylindrical. What will be there? Electric field intensity at point. Suppose radius of this cylinder is capital R. Then what happens? Spherical, cylindrical, hollow cylinder. Hollow cylinder. Cylinder. Charged. Hollow charged cylinder. See here. If point P lies outside, mean this distance R from the center, R is greater than radius. That time formula electric field intensity E is equal to what? 1 upon 2 pi epsilon naught lambda upon R. If this point P lie outside, P lies outside, that is R is greater than R. If point P lies on the surface, to that time E is equal to what? 1 upon 2 pi epsilon naught lambda upon R. Here R is radius of cylinder. If point P lies inside cylinder, cylindrical cell, or you can say, okay. Then what happen? Electric field at this point, at any point inside, so this is 0, because if you want to make the Gaussian surface, if you will make a Gaussian surface here, so you will see inside no charge, total charge inside 0. So that time what happen? E is total charge 0, electric field intensity will be 0. So remember these things. For hollow cylinder or cylindrical cell. Cylindrical charged cell. Remember, here they have not given surface charge density. They are linearly distributed. Lambda is linear charge density, mean charged per unit length of cylinder. Linear charge density mean lambda is what? Lambda is charge per unit length of cylinder. Cylindrical cell, or you can say cylindrical cell. Remember, so that time if point P lies outside, same formula it will behave like a long straight charged thin wire, 1 upon 2 pi epsilon naught lambda upon R. Just on the surface, R is capital R is radius of cylinder, P is equal to 2 pi epsilon naught lambda upon R. But if point P lies inside, here, this is cylindrical cell, that time E is equal to electric field is equal to 0.